examples of that stuff in class. All right, so 5, 6 is inequalities in one triangle. We've been talking a lot about congruencies. Well, if things are not going to be congruent, then they're going to be incongruent. Okay, congruence led us to equality, right? So incongruence is going to lead us to inequality. Okay, this is the number one kind of concept that we're going to talk about today. Pretty straightforward. Okay, if you pass second grade math, you should know this. If I'm taking two things and add them together, okay, and this says just C has to be bigger than 0, and this is always going to be true. But I want to just address it with, let's just say B and C are both bigger than 0, because that's how we're going to use it in our geometry today. So B and C are just positive numbers, right? If I add them together, is that sum going to be always bigger than either of the individual parts? Yeah, okay. They're saying here in this one that, if I take A is equal to B plus C, but C is greater than 0. So let's say I take, let's say 10 is equal to 8 plus 2. Is C bigger than 0? Did I meet that requirement? This is C, right? Can I then say A was bigger than B? 10 bigger than 8? Yeah. Okay. Even if I do this, let's say that, let's say that I go 4 is equal to negative 12 plus 16. Is that bigger than 0? Is 4, which is my A value, is that bigger than my B? Right? Okay. So that property of comparison saying that if I'm summing two things together, one of them is positive, then my sum is always going to be bigger than that other object. Okay? The way I want to think about it today is if I take two numbers that are always positive and I add them together, the sum 100% of the time is always bigger than the individual parts. You've heard that, and maybe if you're in choir or band or an athletic event or a sport, okay? You've always heard the whole is more important than the individual, right? Okay? The symphony is so much more important than the one flute player, correct? Okay? The football team is more important than the one quarterback or whatever, okay? So that's the same idea here. The angle 1, okay, out there, that exterior angle, is larger or greater than any of the individual components 2 and 3 that are on the inside of that triangle, right? If we stay with what we talked about in chapter 4, I think it might have been late chapter 3, early chapter 4, that the measure of angle 1, which is an exterior angle, it is 100% of the time equal to the sum of 2 plus 3, the remote interior angles, right? Well, that situation right here is saying that you've got A equaling B plus C. C is representing either angle 2 or angle 3. Is that going to be positive? Is C going to be greater than 0? So we're meeting that property in the last statement, right, or last slide. So then that tells me the conclusion I make from that is that A has got to be bigger than B, and or A has got to be bigger than C. And that's what we find out. If I take two angles and add them together, 2 and 3, that sum is always bigger than 2 was, and it's always bigger than what 3 was. Is it okay? Is that pretty straightforward, pretty obvious? I think what you find out, even though the way maybe we apply it and use it later on, in a lot of mathematics, the rules or the theorems that are presented are a lot of times very straightforward, very obvious, maybe almost common sense. Okay? But through then the application of them, we start to see that the way we use them is going to help us explain things that maybe aren't so much common sense. Okay? So that's a nice tool for us. We don't use that a whole lot, at least that one itself a whole lot. We use this property a lot. We use that property a lot. Okay? This is one situation in which we use that property. But then when we don't see a whole lot of questions that deal with looking at an exterior angle and saying it's bigger than angle 2 and it's bigger than angle 3 on the individual basis. It might be something that we use quite a bit in checking our solutions, checking our work. When I find angle 1, I always want to make sure that, was it bigger than 2? If it's not, then I've got a problem. Was it bigger than 3? If not, I got a problem. But other than that, we don't use that property a whole lot. We do use this property a lot, though. We've already seen this. You've already learned this. It says if two sides of one triangle are not congruent. So you got two sides that are different, right? If they're different, you should be able to compare and determine how they're different, which one's bigger, which one's smaller. If you can do that, then the angles opposite those segments are different in the exact same way. Okay? Meaning here, if XZ, if my red segment is bigger than XY, my blue segment, then the angle opposite red, which would be angle Y here, is going to be bigger than the angle opposite XY, which is Z. So Y is going to be bigger than Z because the side opposite Y was bigger than the side opposite Z. You guys remember talking about that in chapter 4? Okay. We talked about it in regards to all three angle measurements or all three side lengths. Okay, but you only need a theorem that presents the relationship between two, because then the next thing we can do is say, okay, let's look at two different segments. Let's look at XZ maybe compared to YZ. Okay, and I can tell the difference between those two, and I can tell then which one is larger, which angle is larger, X or Z. X or Y, I think is what I was saying. I could look to see which one of those angles is bigger, and then now that I've done it 2 times within the same triangle, looking at 2 different sets of segments and 2 different sets of angles, if I go back and think about it, one of those sets of segments was consistent in both comparisons, and then I can use the transitive property to come up with the argument about all 3 segments or all 3 angles. We'll do an example of that in a moment. But the reason I talk about that is because I want you to understand when you see a theorem or when you're applying a theorem, a lot of times the theorem, in math, we like to say the most with the least. Okay? We want to be very concise. We want to say the bare minimum thing we have to say that will be able to be shown to be true and used whenever we need it. Okay? This does not talk about listing all 3 angles or listing all 3 side lengths. But that is kind of how we apply and use this theorem. Okay? So a lot of times we'll take a theorem and maybe analyze it, work around with it, mess with it to see, can I make a maybe further argument, okay, that the theorem is not necessarily stating in its theorem, but is always true based off of that. Okay? I don't know what's going on with my voice. It's just kind of cutting in and out every once in a while. So I think I've hit puberty already, but I'm not sure. So if you hear my voice crack, that's why. Huh? Yeah. All right, so this theorem is the converse. This theorem just says if you can look at the angles, you should be able to make a comparison on the sides. So talk about which angle is bigger, which angle is smaller. Then looking opposite those, you should be able to talk about what side is bigger, which side is smaller. Okay? So I want to kind of do an example of this using directly the theorem, and then kind of talk about how can we maybe cheat that process a little bit. So what the theorem says, if I look at those 2 angles, can you compare those 2 angles? Which one's bigger? Angle V, right? So which segment, TU or TV, is bigger? Okay. So UT is bigger than TV. So I'm going to write it this way. UT bigger than TV, or TV is smaller, right? Does that make sense? The next thing is to say, okay, what if I look at that angle there compared to that one? Okay, well, what is angle T? 60. So now what is opposite 60? UV. So how does UV relate to UT? UV is smaller than UT, right? Okay. So now my final argument is going to look something like this. I'm going to have UT as being the biggest thing, right? Then over here I might have TV or I might have UV, There's going to be an inequality sign here. But I'm not sure right now, does TV go there or does it go there? Does that kind of make sense? I got to figure that out. Well, in figuring that out, now I'm going to compare TV and UV. Well, TV came across from 58, right? UV comes across from 60. So where's TV go? Is it smaller than? Is UV smaller than TV or is TV smaller than UV? TV is smaller. So TV should be all the way to the left in my comparison. UV is the middle one. UT is the one on the right. Does that make sense? My hopes are that you guys see that through that process, the theorem was applied twice. It was applied once looking at just those two and coming up with an argument about those sides. It was then used with those two, okay? And then I guess it was used a third time where we compared those two, okay? That kind of makes sense? But what we see then is that even though that is what the theorem says, you should be able to shortcut that theorem every single time and say, when I'm trying to do this process, okay, if I go smallest to largest, okay, I should always be able to do that based off of these angles. Which one's the largest? 62. So UT is the largest, right? Which one's the smallest? 58. So TV. And then UV falls in the middle. That's the most kind of useful comparison or application of that theorem. It's not to go through the way the theorem was written multiple times. Does that make sense? Okay. And that's what happens a lot in mathematics, is that they're going to give you everything that you need, but they're not going to tell you how to do it with three angles. Okay. They're going to allow you to kind of work things out on your own a little bit and make those comparisons. It's a concept that happens a lot in mathematics. I'm not saying that I explain it real well, but I think that's something that you're going to be exposed to and see quite a few times from here to graduation, or maybe the last math class you take, is that even though the theorem is presented this way, that's the most, or the most simplest way that they're going to write something, and you could take it and you can kind of expand upon it if you need to. Okay? Yes? The TV is the smallest, is like across from 58? Yes. And 58 is the smallest angle.
Oh, so like... So it's not like based on like the fact that like it's 60 and 62, it's 60.
Right. So, I mean, it's in comparison. So, if I look at the 60 right here, right? If I put these angles in order, it'd be 58, and then it would be 60, and then 62, right? So then the side opposite 58, the side opposite 60, and then the side opposite 62 is kind of what we're looking at. That would be the order from them being smallest to largest. Does that make sense?
Yeah.
Sure? Okay. And that type of problem, again, is not stated in that theorem. It doesn't say find the smallest angle, opposite it, you're going to see the smallest side, find the largest angle opposite, you find the largest side, and then the one in the middle is the side that's in the middle. We have to read into that theorem and see what exactly is it talking about. I'd like to show this last one here. If we were to zoom out, all it does is tell us that angle right there is 130. This one here is 24. This one's 26. And the question is, what is the smallest side? What's the smallest side going to be there? Okay? OX or XO. Okay? Now, when I look at those, so what is making that comparison is angle S is smaller than angle X, right? 24 degrees is less than 26 degrees. So then the side opposite 24 should be smaller. OX should be smaller than the side opposite 26, which is SO, right? Does that make sense? Here's my question. What if I subtract 1 from there and add it to there? 24 and 26 were pretty close together, right, initially? So because 24 and 26 are close, OX and SO are pretty close, right? So when I move 1 down and 1 up, what's going to happen?
They're going to be equal.
Yeah, they're going to equate, okay? I mean, not any picture that I want to. I can't just take angles. So I'm saying if this was question number 1, and then question number 2 gave me an angle that's 130, 25, and 25, and I want to make a comparison of side lengths, the comparison, because in here, they're unequal, but when I make these angles the same, the sides become equal. And that should kind of be analogous to what we've talked about already with isosceles triangles, right? Isosceles triangles said if the base angles were congruent, then the sides opposite are congruent. Okay, and that's what we're seeing here. If I have 25, 25 as my angles, then the sides opposite have to be the same. Okay. But no, I can't, and just one problem, I can't just pull an angle, a degree from one angle and slap it on somewhere else. It would change the problem. We good with that stuff so far? I can do the same thing. If I knew all the side lengths, I can work my way back inside to the angles and order the angles appropriately using the same kind of logic. The last theorem, which is the most important theorem, is what we call the triangle inequality theorem. And let me just kind of reset this thing back to, actually, let's do it this way. Let's open a new one. Triangle inequality. All right, so the idea behind this one is if I were to give you like 3 pieces of yarn or 3 like yardsticks, but keep the distances different, okay? Can I always make a triangle?
Not always.
Okay, not always. So we want to investigate the situations in which I can. So what I want to do, I want to take one of these segments, and I'll make it kind of as big as what this applet's going to allow for right now. Make it 12 units long. So that red segment is one of my sides of my triangle, or my triangle. And the blue one and the green one are also the second segment, third segments. Now those second and third segments are going to be able to be moved. Okay, I'm going to keep the red one static. Okay, you could do the same thing just the way I've generated this applet. I can't do it, but you could leave the blue one alone and move the red and green one. Does that make sense? Okay, at least I don't think I can do it. Yeah, I guess I could. I'm just going to leave the red one alone for right now because I think it makes the most sense to do that in regards to kind of seeing this relationship. If these were my segments, I should be able to float them. Okay, when I tell you I want to create a triangle out of these 3 distances, it means take those segments of those lengths and put them endpoint to endpoint and see if you can float those segments to where the third point or the third vertex of my triangle is established by their intersection. Does that happen here? No. Okay. What am I tracing out with that yellow dot, though? Circle. Let's look at that circle. What am I going to be tracing out with that yellow dot? No, circle. Let's look at that circle. What do those 2 circles not do? They do not touch. Okay, they do not intersect. And even if they do touch, we're still having a little bit of an investigation that we have to do. Okay, but when they do not touch, we see that those 2 triangles or sorry, those two segments do not allow us to make a triangle, right? Okay. Now, like I said, you can do the same. Instead of just moving the blue one, say we let the blue one be static, I can move the red one and the green one. It's just kind of harder to kind of manipulate. And we're going to see that there's no way that they would be able to touch either. Okay? So just going back, and for the rest of this, I'm just going to leave the red one alone. Yeah?
Would the two circles have to touch in two different places?
Yes. Because when they touch one time, let's kind of... So in order for them to touch one time, the radii of the two circles have to add up to what? They would have to add up to 12. So if I do this, let's make one of them, just to make them different, let's make 1, 7, and 1, 5. Okay? Now, where do they touch? Be right there where my cursor is, right? So when I bring this segment down, and I bring that segment down, that looks like those 2 points overlap, right? But what I've done with GeoGebra here is just made these points, because points have no size to them, right? So I've made them way too big, just so I can grab them and move them easier. If I do something like that, even at that point, people say, well, they touch. Well, let's zoom in on them. Do they touch?
Oh, no, they don't.
They don't. Okay, so...
That's really tough.
So they don't touch, okay? But if I move them down here, do they touch?
No, they don't.
They don't. Okay? So let's drag them all the way down. Do they touch right there?
Yeah. No, they don't.
How many times do these circles touch? One. So aren't these points on the end points of your radii? So they don't touch, right? Okay. Can I keep doing this game over and over and over again forever, as long as I want? Okay, so eventually, zoom out a little bit here. Back to that red line somewhere. We zoomed in pretty far. This zooming in process, guys, is a calculus concept, okay? Because those don't touch, right? But that looks exactly like what I did a moment ago, right? Just to see if they don't touch, I just now have to zoom in further than what I did before, and they're not going to touch, okay?
Isn't there a certain point where it's defined as touching, like after a certain distance?
So the idea is, so that whatever we want to call that distance between these 2 points, all right, so not touching, right?
No.
Where'd they go? There. All right, so not touching, correct?
I'm hoping you're doing it. I'm not doing a very good job.
All right, so we agree that, let me just stop there. They're not touching right there, correct? Okay, so your argument, so isn't there a point that we're defining? So what we do in calculus is we allow that distance between those 2 yellow dots to be identified as something, okay? Maybe I just call it X, okay? Our goal, our definition of those 2 points touching is what we call the limit of X approaching 0. So meaning that we want that distance to approach 0, and when it does get to 0, that means that those 2 points are touching.
But at one point it's considered to be close enough to 0.
Never. Like it has to be 0.
Technically, if you zoom in enough, my fingers aren't touching. No, that's what I'm trying to
If we get to the point, so right now when I zoom back out, Okay? It looks like my green segment and my blue segment are all on top of my red one, right?
They're not.
Okay? They're not. They're slightly off, okay? But when I do move them on top of that red one, do I have a third vertex? No, I've got 3 points, right? I've got that point in the center of that circle on the left, okay? These 2 points will come in contact and overlap each other, but they're going to be on the same line that point and that point are on, right? So what would you call all 3 of those points if they're on the same line? What's the vocabulary word for saying that points are on the same line? They'd be collinear, right? Okay. So they're collinear. What was the key thing about the definition of a triangle?
3 points that aren't collinear.
3 points that's a figure formed by adjoining 3 non-collinear points with segments. Okay. When they're collinear, we have a collapsed triangle. It does not exist. Okay. And that occurs when the smaller 2 sides sum is equal to the third side. Okay. Now let's look at this. Let's take that 7. I'll make it 7.1. Okay? So did you saw that the circle on the left got a little bit bigger, right? So now my blue segment where it's currently at is overlapping my green one, right? So to fix that overlap, to unoverlap them, take that green one up, take that blue one up, and what do I create? A triangle. Now, Kenny said something earlier about do they have to intersect twice? Yes. What do I create when I do that?
Triangle.
Another triangle. Okay. Now, my argument to you is that distance changed to 7.1, right? Does this work if I go 7.01? Do my circles still intersect twice? You're seeing right there, there's a gap right here between my circles, right? Okay. So we do indeed get a triangle with 7.01. Will I get it with 7.001? Yeah, now my rounding still just shows this 7. If I go rounding to 5 decimal places, 7.001. I could zoom in and we'll be looking at that triangle. Now, just kind of think about it. Is that a very, 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 very shallow or collapsed, small, very, very small altitude for that triangle? Yes, but it's still a triangle. Okay? Because when we want to take 3 distances to create a triangle, we need to abide by what we call the triangle inequality theorem. And the triangle inequality theorem states this. It says the sum of the lengths of any 2 sides of a triangle is always greater than the third side. Okay? The sum is always greater than the third. That is directly what we stated in the first slide, that A is equal to B plus C, then A is greater than B, or A is greater than C. That's what we're saying here. Okay? If I take XY plus YZ, okay, that means that sum is greater than something smaller than it, essentially. Okay. Now let's look at this. Look at just some specific examples here. Now this is true for every single triangle that can be created based off of side lengths. So the question a lot of times is, if you have these side lengths, does that make a triangle? Well, this is a relationship for every single triangle. If we can show that, then yes, we have a triangle. Does that make sense? So if I give you the side lengths of 8, 5, and 11. Okay? 8 and 5 are the smaller 2 sides, right? Okay? So that is maybe this condition right there. Okay? 8 plus 5, is that greater than 11? Yeah. Okay? Now what they're saying is that this relationship should exist as well. I should be able to take and basically interchange one of these values on the left with the value on the right. So let's take the 8 and 11 and let them switch spots. So 11 plus 5, is that greater than 8. Is that obvious? Is that common sense? If I started over here with two numbers, okay, obviously in both situations, the 5 is constant, right? So the 5 doesn't really matter, okay, when I'm doing these two comparisons. It's a common value. If 8 was less than 11, okay, 8 was less than 11. When I move that 11 over there and add it to 5, isn't this sum here greater than what it was here? Okay, so that sum there is going to be bigger than 11, isn't it? Okay, which obviously then makes it a true statement that when I put that 8 there, because 11 plus 5 automatically is bigger than 11, well, then it's going to be bigger than any number that's smaller than 11 as well, right? That kind of makes sense? So what I'm doing, I'm trying to show you there is that if I start with 8 plus 5 is greater than 11, and I interchange those values, I make the 8 get to a bigger value on the left-hand side, and I make the 11 shrink to something smaller. This statement is even more true if you have degrees of trueness. I don't know if that's something that exists, but that is even more true than what this one was, or even more obvious than what this one was. Does that make sense? Okay. So then doesn't it make sense to do the same thing if I go 8, replace the 5 with 11, and put the 5 over here? Doesn't that have to be true? Because that one was? Does that make sense, everybody? So this theorem, again, says 3 things. But in our application of that theorem and using that theorem, we're never going to look at all 3. Okay? Because if we can look at the one, that first one I wrote, 8 plus 5 is greater than 11. Take the smaller 2 segments, add them together. If it's greater than the third one, then those other 2 inequalities are automatically going to be true. And that means then you have 3 segments that make a triangle. Does that make sense? Okay. So in example number 1 there, I do not want you to say, okay, is 4 plus 8 greater than 11? Yes. Is 8 plus 11 greater than 4? Yes. Is 4 plus 11 greater than 8? Yes. And now I know that because I said yes to all of those, I've got a triangle. I want you to take 4 plus 8, add those together. Is that bigger than 11? Yes. You took the smaller 2, add them together, bigger than the third, and that automatically makes the other inequalities true as well. All right, that's a little bit more efficient way of doing it, isn't it? Okay. What about number 2, 3, 4, and 5? Does that set of segments make a triangle? Yep, 3 plus 4, those are smallest ones, right? Don't get in the habit, it's just the way I kind of wrote these or typed these out. Don't get in the habit that it's the first 2 that I'm adding together. It's the smallest 2. So 3 plus 4 is 7, greater than 5? Yep. What about 3 and 3? Is 6 greater than 7? No. So you cannot make a triangle with that. So what's happening there is your 7 would be kind of that segment, and you would have a 3 making that circle, and a 3 making that circle. Will those circles ever intersect? No. Okay, so you don't have a third point. What about 9, 11, and 12? Or sorry, 20. Is 20 greater than 20? 9, 11, and 20. Add those 2 together, I get 20, right? The answer is no there. What's that picture going to look like? Right, it's going to be that straight line. Now your circles are going to be, what was the word we talked about where they intersect one point, one time? Start with the word or the letter T. Tangent. Those circles are tangent. When the circles are tangent, you do not get a triangle. Okay, so if you left with that kind of stuff, those types of questions, and then this is the one that usually is not extremely difficult, but a lot of people have questions on it the first time they see it, so I'm going to do an example of this. It says, what are the limits or the boundaries for the third side? Okay, because if I go back to maybe this image here, let me just reopen a fresh one of these. Maybe it won't let me. All right, so if I look at maybe these segments here, okay, I can make a triangle, correct? out of 4, 4, and 7. Okay. Now the question is, how can I adjust this? Okay, I can adjust that one. Now it's 3, 4, and 7, and now they're not going to make a triangle, right? So the boundary for this one, okay, this one would have to be, this third side has to be a little bit bigger than 3, doesn't it? Okay. But I can't allow it to get too big, because if I allow it to get too big, now does it become the largest side? And now these two are smaller ones, and now those will not touch. Does that make sense? Okay. So there's a smallest that this third side could be, and there's a largest that that third side could be. So I want to go through the process of doing that. Okay. Now, when we do, I want to walk through the kind of logic. There's a really easy, quick way of addressing this. But if I have these two sides, okay, my third side, and I'm just going to call it Z. My third side might be the smallest, 8 might be the middle, and 12 might be the largest, right? Does that kind of make sense? Okay. Could I also have 8 being the smallest, my third side Z being the middle, and 12 being the largest? Or could I have 8 being the smallest, 12 being the middle, and Z being my largest? Does that make sense to everybody? So we've got to figure out kind of the values of Z that set those things up, set those relationships up. So my argument, the first one is that let's just assume that 12 is the largest. If 12 is the largest, okay, Z plus 8 would have to relate how to 12? Must be greater than 12. Okay? So when I assume that 12 is the largest, Z plus 8 has to be bigger than 12. So would that mean that Z is greater than 4? That makes sense to everybody? So there, I just told you Z, my third side, has to be bigger than 4. I just gave you the lower boundary or the lower limit of that third side in regards to its distance. Okay? Now, kind of what happens here is that was assuming that basically Z and 8, so Z was the smallest and 8 was the middle one, right? Well, if I flip it and say Z is now the middle one and 8 is the smallest, will I still get the same comparison? I'll get 8 plus Z is greater than 12. Does that make sense to everybody? Is that going to leave me the same inequality, Z plus 4? Is that right? Okay. So when Z is either the smallest value, 4, or when Z is greater than 4, it kind of addresses these two situations. Okay. Where Z is the smallest value or it's the middle value. But I haven't given you an upper bound yet, right? So if it's an upper bound, so if Z is the upper bound, doesn't 8 plus 12, the smaller two sides, have to add to give me something bigger than Z? So what's that going to give me? 20. 20 is greater than Z. Z. Okay. That's a lower bound. That's an upper bound. Those are limits. Z has to fall between those. You guys remember doing this last year? If I have like 4 there, and I have 20 there, and I said Z is greater than 4, it'd be that stuff there. Said Z is less than 20, it'd be that stuff there. And if I want the and, or I want both those things to happen, it's that solution. So I write 4 is less than Z is less than 20. Remember doing that kind of stuff last year? Okay. That is the set of values that Z is allowed to take on so that we construct a triangle. Now, hopefully, you realize what is the first value bigger than 4 that you're allowed to use there? 4.0000000000000, however many times you can say 0, and then you'll probably die doing that. Somebody else will come along and do the same thing. They'll die. The entire population of the world will do it, and they'll all die. And before the last person dies, they put a 1 on there, and that is still not the first triangle you could use, or first segment you could use. Okay, but it's the first number. It is the first number immediately to the right of 4, which is not 5. Does that make sense? Okay. When we talk about realness, this is the only way we can do this. When we start talking about real numbers, okay? I get a lot of people say, well, if this is my solution here, okay, so that segment is it representing all the distances, all the values between 4 and 20, okay? Well, if I say 5 is the first one I'm allowed to use, do you see how I left out an infinite number of possible distances for that triangle, for that third side? Okay, so 4.3036365, that could be a side of my triangle. So when you see those inequalities, we're talking about real numbers. We're not talking about